is CORDIScovery. Hello and welcome to this episode of CORDIScovery with me, Abigail Acton. The brain, still largely uncharted territory, but it's a great time to be a neuroscientist. Computational modeling, multimodal neuroimaging, and novel brain stimulation methods are producing fascinating new data. Greater computational power, AI, and machine learning are helping to make sense of the information. Today, we're looking at some of the latest research that has made the most of such techniques to reveal how our minds work and how our brains are structured. What makes us decide to behave in a certain way in a social situation? What goes on in the brain when we work out how to deal with a challenge, for example? How do infants read minds to predict the actions of the people around them? There's an essential conundrum to this question that our guest will reveal. Left or right-handedness, language and communicative gestures, how do they relate to the symmetry of the hemispheres of our brains? Can MRI images of baby baboons shine a light on brain asymmetries, given that monkeys are non-linguistic but very communicative? Curious? Our three guests, each of whom have been supported by EU funding, will share their understanding of these and other intriguing questions. Christian Ruff is Professor of Neuroeconomics and Decision Neuroscience at the University of Zurich. A key goal of his work is to uncover how the brain navigates complex social and moral situations to understand the reasons behind individual differences in these behaviors. Welcome, Christian.
Hi, Abigail.
Hi. A professor of developmental cognitive neuroscience at the University of Copenhagen, Victoria Southgate studies infant social cognition and is particularly interested in how infants think about the self and the other. Hi, Victoria.
Hi, everybody.
Adrian Megadichian is a comparative psychologist at the Center of Research in Psychology and Neuroscience at the National Center for Scientific Research in France. He has worked with wild chimps in Senegal and on brain MRI studies in the US as part of his goal to understand how communication shapes the brain. Hello, Adrian.
Hello, thank you for the invitation.
You're very welcome. It's good to have you. Christian, I'm going to turn to you first. The Brain Codes project set out to better understand the brain mechanisms that enable us to control our social behavior. Can you tell me a little bit about the novel methods at the fingertips of neuroscientists? It's an exciting time for the field.
It definitely is, Abigail. In terms of brain processes, we can measure with various things like fMRI and EEG where in the brain and at what specific point of time during our actions neurons are active. So that's exciting, but we do need to know, of course, what to look for as well on the behavioral side. So here, if we want to understand particular motives that may drive behaviors, we now have specific experimental paradigms and computational models that help us at any moment of time to try to simulate and basically predict what motives are driving people's behaviors. So we can relate that to the brain activity that we measure at the same time. And then the final piece of the puzzle is we can also influence the brain. So there's methods like TMS and TES, where we apply weak magnetic fields or electrical currents to very briefly and reversibly alter the function of the brain. And then we can see whether behavior really changes as we would predict.
That's fantastic. Could you just tell us what TES and TMS are in full?
Transcranial magnetic stimulation and transcranial electrical stimulation.
Excellent. So these are obviously tools that are unlocking a lot of things that previously we weren't able to identify or analyze. Your project was interested in what drives social decision-making processes. How did you go about using the methods that you've just described now to see what brain networks are involved in these processes?
So as I said, we have these behavioral paradigms, which are really like standardized situations in which we have people interact with one another. We change the situation so that particular motives like wanting to be fair or wanting to trust someone or telling the truth or so need to be expressed in that situation. And we can see how people do that. So in one experiment, for example, participants come to the lab and they know that they get money that they now have to distribute between all the people in the lab. That's the payment for everyone. It's real money, right? So, and then they have to choose, do I want to get, for example, 35 francs and the other people get only 5 francs? Or am I willing to accept that I only get 30 francs, so a reduction in my payout, but the others get 15, for example? Right? And then we vary all these different payoffs, and we can basically see how much people care about fairness and relate that to brain activity, but then also to see how stimulation of particular brain areas changes how much people care about fairness.
Oh, that's fascinating.
So that was one line of work. But in another line of work, we were also interested in something that I guess Victoria cares about a lot, theory of mind. So how we understand other people's intentions. So what we did is we had people play rock, paper, scissors with one another. And then based on economic theory, you can computationally define different strategies. You can focus on yourself. So say, I like playing rock. Not a very good strategy, but you could do that. Or you can observe what the other person is doing and say, oh, the other person always plays rock, so I'm going to play paper. Or you can try to basically deceive the other person. So you can say, I'm going to play rock. So they think I play always rock, they'll play paper, and now I play scissors. So by fitting these models, we could determine at any moment of time what strategy someone plays and how flexibly they can change it. And we could identify which brain processes are necessary for both of these particular strategies, but also this flexibility in changing strategies.
I think that's wonderful. That's and all of that in real time as well. So
exactly.
Yeah, fascinating. And what were some of the key findings that you were seeing?
So some of the key findings for the theory of mind line of work, for example, was that one specific brain area, the temporoparietal junction, was causally necessary for being able to mentalize, so to understand what someone else is doing and making them believe you're going to do something. So when we stimulated that area, people became predictable. They couldn't really lead others down, actually, the path of thinking that they were always going to play rock. In contrast, pattern of activity across the whole brain was necessary for changing strategy. So that was not one brain area. That was a whole pattern of interconnected brain areas. But that pattern is really robust. So if we measure that in one group of participants, we can get another group of participants into the lab, simply measure how strong that pattern is in them, and then we can predict how flexible they will be in applying theory of mind and changing strategies.
And how do you hope your work will feed into further research or clinical situations even?
Yeah, so I think the clinical application was a major motivation, in particular this causal bit that we wanted to really show that stimulating brain areas, stimulating brain processes changes the behavior. To me was really the prerequisite for saying these could be what lies at the heart of symptoms, say in psychiatric disorders. And for example, the theory of mind work we did a study also with Asperger patients, so patients who basically have a mild, high-functioning form of autism. And the general theory was always that these people are in a way mind-blind. They cannot understand naturally, like many other people do, the thoughts and intentions of others. So they approach situations like this in fundamentally different ways. What we found with our approach is that that's not the case. So they actually showed the same pattern of brain activity and used the same computational processes to guide their actions. They were just fundamentally slower, very, very slow. Yeah.
Okay.
And so when we communicated that also to the people, they said, yes, this feels about right. The social world is just happening too fast around me. So we're really hoping that with these tools, with these measures, for example, you could track whether a particular therapy is efficient, for example, or perhaps even with the stimulation stuff, what you would have to change in the brain, perhaps by therapy or pharmacology or whatever, to help these people.
Oh, that's wonderful. That's really, really interesting. Yes, excellent. Thank you, Christian. Thank you very much for presenting that. That was very clear. Does anyone have any questions or observations? Yes, Adrian.
Yeah, I was just curious about the experiment. So if I understand correctly, the participant, when they do the task with other one, they wear the EEG or the TMS in the same times, right? I mean, so it means that you can actually disturb some temporary, some brain region when they're actually doing this social task?
Exactly. So we have a laboratory where up to 16 people can sit there on their individual computers and interact via the computers. And we can have electrodes on the heads of all of these participants and stimulate each of them with a different protocol. Yes, exactly.
This is very impressive. And I was curious, like you say something like, can you disturb actually the decision by, I don't know, does it affect their fair choice when doing their parallel and make actually a not really friendly choice when you disturb some region of interest?
Yes, so that's possible. What I find even more encouraging and interesting about it is that with certain pulse protocols, we could also increase moral behavior.
Oh.
So, for example, we did a study where we made people more honest. So we put people in a situation where they could lie, for their personal benefit. They basically gained money
and they didn't
by lying. Yeah, and like with the stimulation, they became more honest. Yeah.
That's fascinating.
Wow.
Oh, brilliant.
It's magic.
Thank you very much. Victoria, you wanted to ask something as well. What would you like to say?
Yeah, no, I was just wondering about your findings. You mentioned the TPJ, or the temporal parietal junction, and I was wondering what you think that it's actually doing in these studies. So is it, so you talked about rock, paper, scissors, and I was just wondering whether is it involved in sort of evaluating or figuring out what the other person is going to do, or is it more about strategizing what you might do in response, or do we just not know?
So in our experiment, the TPJ responded always when the strategy of leading someone else into believing that you were going to play something, when that didn't pan out. So when there was a violation of your expectation that the other person is going to react to your behavior. Mm-hmm. That's why we called it mentalizing, a computational definition of it. The technical term is a prediction error, a second order prediction error.
Mm-hmm, mm-hmm. Yeah.
So I play rock, and I expect that that's going to make you believe that I play paper. But if your behavior tells me that you didn't believe that, that's when the TPJ became active.
Interesting.
Isn't it? Isn't it fascinating?
So, I mean, that's why I think this computational modeling can really help us, because I think it's been this conundrum in social neuroscience. What's the temporal parietal junction doing? It's a fascinating brain area. And it's involved in so many different aspects of social behavior, but we really need to pin it down in these types of situations to get a bit closer to the information processing that's happening in that area.
Yeah.
Brilliant. Well, thank you very much. That was fascinating. Victoria, I'm going to turn to you. Socialization and learning depend on making the right inferences about other people's thoughts. The DevoMind project used neuroimaging to improve our understanding of how infants mentalize. So, Victoria, the social interaction we've been talking about earlier depends on making the right inferences. Can you tell us more about how that plans out for children, for very small children, and the sort of age of infants that you were looking at?
Yeah, so I mean, historically, there had been this view in the literature that it wasn't until about the age of 3 or 4 years that human children were able to think about other minds, right? And do this sort of, strategizing. What should I do? What are you going to do? So this was the sort of historical view. And then there came a bunch of studies, some of which I was involved in as well, where we found that actually, if you make your experiments into non-verbal paradigms where you can just look at what do infants expect is going to happen based on how much they look at something. And we have this term violation of expectation, where we ask, okay, what does an infant expect? And if their expectations are violated, we expect that they will look longer at one outcome than another outcome. So studies were starting to show that actually, even though 3-year-olds would make the wrong inference about what someone else will do if they, for example, have a lack of knowledge about what's happened. Babies would look longer at outcomes that would seem to suggest that the person had knowledge that the baby should not expect them to have. So in the context of what we call theory of mind, this is usually tested by you tell a little story like, there's 2 characters, Sally and Anne, and Sally places her ball in the box, and then Anne comes along when Sally's disappeared and moves the ball from the box to a basket, for example. And then you typically ask children when Sally comes back, where's she going to look for her ball? And before the age of about 4 years, children will say she's going to look for the ball in the basket where it now is, rather than the box where she left it.
Do they assume that she has this knowledge even though she can't possibly have it because they have it?
Well, that's the interpretation. Of course, we can't know that because you can't ask children, why are you answering in this way? But the standard interpretation is that they are egocentric. So they know where the ball actually is. And we assume they just extend that to others, that others must know the same thing. So that's generally what we call egocentrism. It was a Piagetian term. By Jean Piaget coined this term egocentrism, and it was assumed that children had to grow out of this at some point. And so the findings with infants were suggesting that they were actually having the correct expectations about where, for example, Sally will search for her ball, and they were showing us this by looking longer at an outcome where Sally searched in the place where the ball now is. So this was sort of the background of this.
Right. So, I mean, if I could use the word surprise, they indicated to us that they were, I'll say surprised, it's probably the wrong word.
Yeah, this is what we also say in the literature, that they're surprised, yeah.
They're surprised that, yes, it doesn't conform to what they're anticipating is going to happen.
Exactly.
And so essentially what we're saying is that the tiny infants seem to be indicating a sense of surprise at something which actually older children don't find surprising because of a perception of egocentricity. Okay. But yes, indeed. And that's the conundrum I mentioned right at the top of this in the introduction. So tell me more. What did you do to go about trying to understand and unraveling this apparent?
Yeah, so this was sort of a big puzzle in the literature, and people would argue back and forth about what this might show. You know, there were different explanations, but there was nothing really very satisfactory. And there were two things that I think were wrong with our initial interpretation of the infant data. So we were giving these, interpretation of the data that, infants were really understanding what the other person thinks, and they were aware when her belief was false. They knew what the reality was, and they were aware that her belief was false, and they were making the correct expectations about where she would search. And I think that at some point I started to feel that this cannot be the explanation because of what we know about the infant brain. So we know that infants are very poor at managing different representations that sort of conflict with each other. So they're really not good at this. And we know that this ability to manage conflicting representations requires something called our inhibitory control and our executive functions, which are really poor in babies. And the other thing is this idea that infants are egocentric sort of implies that they have this self-representation, that they can think about what they think and they can compare that with what someone else thinks. And we also know from developmental psychology that this ability to think about the self does not really emerge until the second year of life. And so the idea that, these 6-month-olds, which is the age at which some of these findings had been reported, including some of my own, were doing this kind of thinking about the self and also managing these conflicting perspectives just seemed very unlikely. So that was the impetus for trying to think, okay, what else could be happening with these babies? And that's when we started to think about this idea of autocentricism, which is the idea that as opposed to being egocentric, where things are sort of anchored to the self, this is where things are, your encoding of the world and how you think about things is really anchored to other people.
So Victoria, what experiments did you conduct in order to try and unravel this?
Yeah, so there had been some work, mostly with adults, showing that adults have a sort of altocentric susceptibility where, if you're asked to judge something, if you can see that someone else has a different perspective, your judgment is impeded to some extent, or the opposite. So we knew there was sort of something that cognition was susceptible to other people's perspectives. So we knew that adults, readily encode and represent other people's perspectives, and sometimes it can interfere with your own representation of events. And so I thought that maybe this kind of altocentric mode of cognition would make sense to, if infants actually began life in this way and they became egocentric as the self-representation developed. And this would fit with many, many findings. And this would predict that if you had a situation where you have a conflict of perspectives, so where the baby thinks, for example, the object is in location A, but they have seen that another person has seen the object in location B, our prediction was that infants would actually have a stronger memory of the object themselves in location B, where the other person thinks it is, than in location A, where the baby has seen it is. So that was our sort of fundamental prediction.
And what did you find?
We found actually more or less exactly that in a situation where there's a person sitting opposite the baby, and there's two sort of boxes in front, one on the left and one on the right, and the baby and the person together see the object move, for example, into the one on the left, and then now the other person on the screen disappears, and so now the baby's alone, and now this object moves from the location on the left to the location on the right. And then the person doesn't come back, but now we reveal the object to be absent, either at the location where the other person should think it is, or at the location where the baby should think it is. And what we find is that babies are more surprised when the object is absent at the location where the other person thinks it is. whereas they should be more surprised at the absence of the object at the location where they have seen it.
Right. Of course, that's the equivalent of an older child saying, yes, it's going to be, Sally will know that it's in the basket, when, of course, Sally can't possibly know that it's in the basket because they've been out of the room. So the baby is exhibiting the ability to recognize where the subject would think the thing was. Right. Okay.
Exactly. Yeah. But it's a bit more, so we actually have a slightly less rich interpretation, that we don't really think that the baby is thinking about where she thinks it is. It's more, we think that what babies are doing are just using other people's attention, the direction of other people's attention, to sort of hone in on what's important to pay attention to. Because when you're a baby, especially when you're very young, you can't really navigate your environment. Your motor skills are pretty poor. You sort of just sit there and watch other people do things. And so we reasoned that what was important for babies at that age was actually to pay attention to what other people are paying attention to. And so we don't necessarily think that babies are thinking about what she's thinking.
Right.
It's just that other people are a good cue to what the baby should pay attention to. What we do know is that by this finding that I just told you about is a finding in 8-month-old babies. And we know that by 12 months, this has disappeared. So by 12 months, babies don't show this altocentric bias anymore. And that obviously coincides with an increase in motor capabilities and in walking and being able to sort of, pay attention to things that are important to you because you're now navigating your environment. So that is one thing. Yeah.
Thank you very much, Victoria. That's fascinating. Does anyone have any comments or observations to make to Victoria? Yeah, Christian.
Yeah, this is really fascinating. I was wondering, as a father of 2 children, I had the feeling that very small babies are not always just attending to me. They're very egocentric in certain situations, for example, when they're hungry or when they're grumpy or when they're tired or something. So I wonder, do you think this altocentric perspective is constant? Or do you think that the babies basically just fluctuate between periods where they're completely focused on their body and their own well-being, and just when everything is fine there, then they're completely with the other person?
Yeah, I really don't know. I think this is a sort of question about how this self-representation develops and how, and we really don't know anything about this. So one of the things that I didn't mention is that we think, and we have data, that this switch between this altocentric and this egocentric mode of cognition happens at around 18 months, when infants develop this self-representation that we can show with things like mirror self-recognition.
Thank you, Victoria. That was excellent. I'm going to turn to Adrian now. Adrian, how do left and right-handedness, language, and brain asymmetry all tie in together? The Just Image project considered how communication shapes the brains of humans and monkeys. So can you tell us what is meant by brain asymmetry and what the current thinking tells us about the functions that involve the left and the right hemispheres?
It's a good question. Brain asymmetry apparently is just a division of labor of the brain between the 2 hemispheres. So there's some hypotheses like proposing that it's a way to optimize space in a limited box to divide the labor between these 2 lobes hemispheres. So and we are very interested in asymmetry because we are very interested in language, and we know that language is very specialized. Most of the function is specialized in the left hemisphere, and some of them are more in the right hemisphere, like the musicality of the voice. We call it prosodia. But semantics, meaning of language, syntax seems to be related to the left hemisphere in the majority of person, and some person also have the opposite patterns, and they are normal. It's fine. It's just that the distribution of some variability between a person. But I would say like 98% of people have language in the left mostly.
Okay, and how does that relate to whether you're left-handed or right-handed? Brain asymmetry, rather.
Yeah, it starts from that because before it was considered that handedness was a good predictor of language lateralization, meaning that the left-handed people have the language in the right hemisphere and majority of right-handers has language in the left. But it turned out it was not true. Like 70% of left-handed people has also language in the left. So it means that we have to find other behavioral cues to infer where is language in the brain. And that's how our project was about. It was to test the idea that, maybe communication with gesture, with the hand, might be asymmetric. You might have some different hand preferences when you communicate, regardless of your handedness biases. You see what I mean? So, and this hypothesis came from our research in baboons, actually.
Okay, so let's just clarify. I can only think of a rather vulgar example. It's the one that just jumps to my mind. But if you think of a very angry driver who has been cut up or something in traffic and has a negative response to using a hand gesture, they might use the right hand even if they're left-handed. Is that what we're saying?
Yeah, kind of. I mean, we cannot measure that actually, but I mean, it's a slight effect. It's not like that clear. But there's this idea that if you're left-handers and you have your language in the left hemisphere, the idea that language is multimodal. It's not just speech. It's involved through your hand movement. When you communicate, it's part of the same systems. So if you're using as a left-hander, the left hemisphere to do gesture, it will slightly move, favor the use of the right hand. That's the idea we try to measure. And this is what we actually find in baboons. And that's why we want to test it in humans then.
Right. Okay. So tell us more about your work then. So this is what you were looking at. This is what inspired your curiosity. So how did you go about your research? What did you actually do in the Just Image project?
Yes, the idea, I mean, I'm a primatologist, so the idea is to study gestural communication, hand movement for communication in baboons, and it's fascinating way of communication. And it turned out that using the hand for communication was sharing in baboons seems to share many properties of language. That's why we're intrigued by this system. And because we know that language is asymmetric, we wanted to see if gestural communication in baboons will involve the same hemispheric specialization of the brain than human language. You see what I mean? So the first thing we observed a long time ago, it was just that when baboon communicate with the hand, they use more the right hand compared to their handedness for non-communicative tasks. So there's something is going on with communication in baboons when they communicate. They seems to involve more the left hemisphere because they gesture more with the right hand. So that was the beginning of the hypothesis we wanted to test with this Just Image project.
Okay, and what experiments did you run in the project?
So then the idea was to try to get some brain images to test this hypothesis. It was a bit funky to try to bring some baboons into an MRI. So we are observing behavior in the social group. So we actually have to catch the baboons for which we have some handedness measure for communication versus non-communicative manipulation task. And then we brought them to the big city at the hospital when they have an MRI to get some picture of their brain and then bring them back, of course, in the same day to their social group. So we could get this nice set of image. And then we just did something very simple, was just to measure the size of some region of the brain in baboon that are homologs to language regions. And that's how we could quantify brain asymmetry in baboons. So, of course, they are sleeping, the baboons in the MRI. We cannot ask them to do gesture in the MRI. Hey, can you make a gesture right now? So we didn't measure brain activity. We just take a picture of the anatomy of the brain.
But you've been doing observational studies on the same subjects, on the same baboons prior in social situations. So you knew baboon X had a tendency to display certain behavior, and then you wanted to see how the brain was structured is the wrong word, but the asymmetries in the hemispheres.
Yeah, it was easy. We could just make two groups, the baboons preferring communicating with the right hand versus the baboons preferring communicating with the left hand, and just see how their brain looks. And it turned out that the brain asymmetry, especially only for region homologue of language, not the other one, only the very famous one in humans, was turned to be predicted by the hand preference for communication only. And so it means that baboons communicating with the right hand, they have more Broca's area or the planum temporale, just bigger in the opposite hemisphere, the left one. And it was almost the other way around for the baboons preferring communicating with the left hand. So we find the links between, in a non-invasive way, we could actually make some links between communication with the hand and language homologue region in baboons. So which means that we might have irritate this brain organization, and it seems that the language might have some deep origins in your common ancestor, like 30 million years ago, thanks to the hand. That's the idea.
Isn't that fascinating? That's absolutely brilliant. I love it. Thank you very much. That was beautifully explained. Thank you. Does anyone have any observations or comments to make to Adrian? Yes, Victoria.
It's super interesting. I was just wondering, I assume this laterality is something you think is innately specified, right? It's not something that is acquired through, different cultures in the different groups of baboons or something like that.
Oh, that's a very good question. I will respond that was actually your question. does gesture is already set up. Gesture asymmetry for communication is already set up at birth. That's why we also scan newborns baboons when they do not gesture at this age. They're only breastfeeding. So we have the measure of their brain, and the planum temporale, for instance, which is a key region for language in human, is already very leftward in the brain in the newborns baboons. So what we did to test your hypothesis, like, is it already set up at birth? We just wait that the newborns grow up and finally start to have an age of being able to gesture. And then we find that, okay, the early brain asymmetry when they were newborn was predicted the hand they're going to use for communication. So it seems to be rigid phenomena. But we find exactly the other way around for handedness, for manipulative action. So this seems to be much more plastic, not just the hand behavior, but also the brain plasticity in the motor cortex. So we find exactly the way around that.
Okay.
Depending of the cradling of the mother, that will affect the hand use of the baby, and depending of the new behavior they're gonna explore, it will affect also the manual, and then it gets stable finally.
Right. So when it comes to non-communicative hand use, it's much more plastic.
Yeah.
Isn't that fascinating? Thank you very much. Christian, you had an observation or a question.
Yeah, thanks. This is really interesting. So you seem to suggest that there's an evolutionary ancient system that's there at birth that's used for communication and that extends to hand gestures and in humans then also vocal utterances, right?
Yeah.
So I always ask myself, why are there cultures like Italy, for example, where people communicate a lot with gestures, whereas if you now go to Scandinavia, so people will really not do it. What do you think is the brain cause of that? Or do you think it's just that the same system just gets used in culturally specific ways?
Yeah, I'm pretty sure even in culture, when you don't gesture, you can measure actually some muscle activation. Yeah, I would say this is definitely some related to some cultural difference, but that will not affect the idea that language is multimodal. And actually in North Europe, they did some measure about the importance of the hand and the links with mouth movement or speech, and it seems to be pretty robust phenomena that is not that is still there in the brain.
Well, thank you very much. You've all explained your work in a way that's very transparent and accessible, for which many thanks, because I know it's quite fiercely technical, but we've got a clear idea of what you've been looking at and what you found, and I'm very grateful to you all for that. Thank you.
Yeah, thanks for having me, and thanks for all of you. It was really interesting.
Wasn't it, Christian?
Yeah, thanks so much. It was really interesting.
Bye-bye, Victoria.
Yeah, thank you, Abigail. I had such a great time. Bye-bye.
Bye-bye. If you end up chatting to someone about podcasts you're enjoying, why not mention CORDIScovery? Follow us on Spotify and Apple Podcasts and check out the podcast homepage on the cordis.europa.eu website. Subscribe to make sure the hottest research in EU-funded science isn't passing you by. We've talked about the use of drones to check for fire risks on board ferries, the latest advances in forensic science, and how to recreate the smells of the past. In our previous episodes, there'll be something there to tweak your curiosity. Perhaps you want to know what other EU-funded projects are doing to improve our understanding of how our minds work. The Cordis website will give you an insight into the results of projects funded by Horizon 2020 and Horizon Europe that are working in this area. The website has articles and interviews that explore the results of research being conducted in a very broad range of domains and subjects, from agronomy to astronomy. There is something there for you. Maybe you're involved in a project or would like to apply for funding. Take a look at what others are doing in your domain. So, come and check out the research that's revealing what makes our world tick. We're always happy to hear from you. Drop us a line. editorial@cordis.europa.eu. Until next time.